So, our final topic in the study of gravitational collisions and deflections is this idea of gravitational focusing. This is essentially what happens for very large angle deflections or very small impact parameter, right? Very close approaches between two bodies. We know that this is less important than the summed effect of many, many weak small angle collisions, but it can still sometimes happen. And when it happens such that the two bodies actually physically collide with one another, impact one another, then it can be a really important thing. So you need to know when that's going to happen. Right. So we'll talk about the general theory of it, and then we'll talk about some applications. Right. So apologies for going back to basics, but let's go back to this basic idea of the hyperbolic orbit, right? We've got two bodies approaching one another from an infinite distance at some constant speed. And if the bodies are of identical masses, then you can easily look at this sort of symmetric situation with respect to a center of mass frame, where the center of mass is just the geometrical center between the two. They approach each other not along the line of centers, but with some sort of global angular momentum. So there's an impact parameter. And if they are attracted to one another, then that means that the distance of closest approach that I'm showing as r sub c here will be less than the impact parameter. Right. So we'd like to know, will these two things actually hit one another? That means we have to take into account the finite sizes of the two objects, capital R. And if this r sub c, distance of closest approach, is less than 2 times r, right? If they basically come together, and if that distance is less than 2r, they will collide. If it's not, they won't. Okay, that's the criterion we want. Now, what actually happens depends on the masses and how much gravity they exert, right? If the two masses are very small, then there's not going to be much deflection at all, right? They just fly right by each other. There's no change in their orbits, right? This is the weak collision, small angle collision limit. And the distance of closest approach is just the same as the initial impact parameter. Right. So if that's the case, then the criterion for collisions is that the impact parameter itself has to be less than 2 times r for them to collide. But again, if the masses are larger, then there will be more focusing. And interestingly, even though the focusing decreases the r sub c, we can think of it as increasing the cross-section for direct collisions, because the cross-section just asks, at an infinite distance, is there going to be a collision or not, hit or miss? And if there's focusing, that means you can start off at a bigger impact parameter and there will still be a collision, right? So bigger cross-section when you're just looking at the initial conditions. All right, how can we do this? We could go through and we could integrate equations of motion again, but we can actually learn everything we need by just looking at the two constants of motion, the two conserved quantities, total energy and angular momentum. And we can go back to the same way of writing it that we did for the two-body problem. We can look at the equivalent one-body versions of these quantities. So for the energy, we just have the 1/2 mv squared, where little m is the reduced mass, v is the relative velocity. And we've got this equivalent one-body version of the gravitational potential energy also. And the sum is a constant. And what we can do is write that, take advantage of the fact that it's a constant by equating the energy written in two different limits, right? We can write it when the two bodies are very, very far apart, and we can write it when they're at their closest approach. So when they're far apart, the gravitational potential is 0. The kinetic energy is just written as, if the reduced mass little m is just big M over 2, if they're identical, this will just be 1/4 times the individual mass times the relative velocity at infinity squared, just the kinetic part. Then at closest approach, we know the particles are going to be moving faster relative to one another at the closest approach than when they're far apart. That's just also the vis viva equation. So there's a maximum velocity that they'll be flying past or trying to fly past one another at closest approach. But then because they're at a finite distance, finite separation, you've got to include the potential energy term also. This is nice, but if we can consider the properties at infinity as the known quantities and the properties at the closest approach as unknown, we still have two unknowns, Vmax and R sub c. So we need a second equation. Well, that comes from the angular momentum. I'm writing this just in terms of the angular momentum in the inertial frame or in the center of mass frame, rather than using the equivalent one body little m and little v and little r. I guess it could have been done using those too, but it is actually kind of symmetric to think about the center of mass version of that, because the cross product Ri cross Vi, and there's really just two of those, because this is a nice symmetric system. So whatever you get for body one, you'll have the same thing for body two, and this sum is done easily. But the cross product just can be written as the velocity at any given time times the component of the distance that's projected perpendicular to the velocity vector. And I'm writing it that way because if you go back to the picture, it's pretty straightforward to see what those are, right? When it's far away, that projected distance perpendicular to the velocity vector is just the impact parameter. When they're at closest approach, that's just R sub c. Okay, so yes, so we can again go through this and write L when they're at an infinite distance versus when they're at the closest approach distance. The 2m is the same in both cases because the mass is conserved. As I just said, when they're at an infinite distance, this perpendicular r is just the impact parameter, well, over 2, since we're measuring it relative to the center of mass frame, but I guess these over 2's are the same on both sides also. And then when they're at closest approach, it's rc, but then the velocities are different in those two cases as well. And they come together to tell us, to give us a relatively simple expression for how the Vmax and the V infinity relate to one another dependent on where the particles are. So that's reproduced up at the top here again. And of course, we can see that our intuition sort of makes sense. If it's a strong focusing effect where gravity plays a major role, then that means that R sub c will be small compared to the impact parameter. B over RC will be big. That also means V max will be much bigger than the velocity at an infinite distance. If it's a weak deflection where there's not much actual focusing happening, then these fractions on both sides here will be close to 1, right? B won't, be reduced that much at the distance of closest approach, and the velocity won't change that much either. Okay, so now we have a separate expression for Vmax as a function of R sub c and the other known quantities. So we can plug that back into the energy conservation equation. Now, if you look at this, you can actually solve it for R sub c in terms of everything else that we know. That would be a quadratic equation. The solution to a quadratic equation is sometimes not the most intuitive thing to look at. And it turns out that solving for a different parameter will end up being more useful. So let us actually solve for the impact parameter B as a function of R sub c. Now it seems like we're turning it on its head, and we are, but we'll see how that's a useful thing to do. So it's easier to solve for B because it only appears once here. So you can basically bring everything over and solve for B. And now we can write B as a function of the closest approach distance and the masses and the velocity at infinity. And again, this sort of makes sense for if we look at if the masses are small and there's not much deflection, then this second term under the square root is negligible, and it's just B is roughly equal to R sub c, right? No deflection. But when there is a lot of deflection, B will be bigger than RC, as we know it should be. All righty. Why is that useful? Well, if we want to actually ask the question, will the stars impact or not? We already know what the condition is for a physical impact. R sub c has to be less than 2 times the physical radii of the two objects. So why don't we just plug in 2r for little rc, and this gives us a collisional impact parameter, or an impact parameter, that you can define in terms of the things that we definitely know about the system: the sizes of the stars, the masses, and their velocity at an infinite distance. And now we can just compare that with the with some guess for the impact parameter, right? If the impact parameter is bigger than this critical value, then they'll never collide. If it's smaller, then they will collide. All right. Right. So the collision criterion is, if the B you choose is less than this thing that you can calculate, it'll collide. And we also know that this B collision is larger than the weak gravity limit, right? That would be just 2r, which we said that if there was no deflection, the impact parameter just has, the critical impact parameter is just equal to 2r, which ensures an impact. Yeah, so that's sort of a useful way of thinking about it. We can simplify this term under the square root a little bit, because if we have a spherical star, this 2gm over r is just the square of the escape speed. So we can write this second term as a ratio of squared velocities, escape velocity over the relative velocity at infinity. And then of course we can compute those quantities to figure out how important that second term is in typical cases. For a regular solar type star, the escape speed from the surface is about 600 kilometers per second. But if you look at a typical globular cluster, the relative random speed of stars with respect to one another is only about 10 kilometers per second. So this ratio of v escape squared to v infinity squared is going to be large. It's something like 3,600. So it's a very important factor when looking at the relative interactions of stars. The other thing that we can talk about is that now we have a hit or miss condition. We now know, if the impact parameter is bigger than this B collisional, it will miss. If it's smaller, it will hit. So essentially, we can use this language of cross sections for figuring out whether there's going to be a collision or not. So we can write the collisional cross section in terms of these known quantities, and we can use the same trick we did for large angle collisions in a plasma to figure out how often they happen. We can just use this straightforward geometrical definition of the collision rate, which is 1 over the mean time between collisions, just as the number density times the velocity times the cross section. Of course, you see that these things eventually give you a 1 over time type quantity. And we can think of this V infinity as just the most probable relative speed, maybe the thermal speed of randomly moving stars in a cluster or a galaxy. Yeah, so now this is given us an expression for the collision rate. Now, you could go through and do this more exactly if all the stars weren't just at a constant speed difference between them. Say if you had a Maxwellian distribution of speeds, Binney and Tremaine works that out, and you basically replace this V infinity with the thermal speed with some other factors out front. You essentially get the same thing. You get some numbers times a number density times the thermal speed. The collision cross-section has an R squared, in it because it had a B collision squared, and then it had that square root quantity, which we now squared. And this second ratio quantity is often called the Safronov number, because he first applied it to the protoplanetary application that we'll talk about in a little bit. We can also sort of close the book on looking at, say, globular clusters, which we know their number densities and we know their other parameters. and we can work out that the collision rate is actually kind of long. You know, it's longer than the age of the universe. It would be actually longer. The rate would be lower if we didn't have this gravitational focusing term. But yeah, no, it's still relatively long. And, you know, it's several orders of magnitude longer than the relaxation time that we worked out in the previous video. And in fact, Binney and Tremaine shows that you can relate the two, just like we related the new small angle and new large angle, those two different versions of the two different components of the total collision rate in Coulomb collisions, right? It had to do with the Coulomb logarithm. It's a little bit more complicated for the gravitational focusing problem, but yeah, you can show that this ratio is about 100, as we've seen here. So yes, the large angle collisions are generally less important than the sum defect, this relaxation of many small angle collisions. But there are times when it's important, and we can look at certain applications to see when it's important. I won't say much here in the video, but there's about a page of content in the lecture notes talking about what happens in the cores of galaxies or globular clusters, right? You can sometimes have enough things collapsing together to form a supermassive black hole, but sometimes you can have many individual stellar collisions, and you can see the hints of those happening in globular clusters. I talked about blue stragglers last time. So yeah, I don't have too much time to talk about that and everything else. I do want to go through the planet formation process in protoplanetary disks, because that's an interesting application of this focusing theory. And then I'll just have one slide at the end on another thing that we've observed in our own solar system that exhibits gravitational focusing right now. But the first, I guess the main application is this protoplanetary growth model, because we're talking about actual collisions between bodies. And in the early outer parts of the solar system, when things are sort of cold and icy, each of those direct collisions actually stays there. And protoplanets can actually grow in time by undergoing multiple gravitationally focused collisions. So we can look at the we can look at the growth rate, the mass of a protoplanet as a function of time. What is that rate over time as multiple collisions happen? You know, it's sort of a stair-step thing, but overall, averaging over many things, you can write that as the mass of each planetesimal that gets accreted onto the surface. And if that happens every so often, every collisional time that we just derived, then you can just write this right-hand side as m over t collisions. Now, I'm being a little, playing a little fast and loose by using this capital M in different contexts, because on the left, we're following the m of t as of the growing planet as it's growing, but on the right, this m, I'm using the mass of each little red, as in these cartoons here, planetesimals that get accreted on to the planet. I hope the use of which use of m is going to be clear in context, but soon we won't have to worry about it because we can sweep some of them under the rug here. So we can write this right-hand side as an m of the planetesimal times 1 over the collision time, which in the earlier slides we saw can just be written as n times v times a cross-section. Now the m times an n here's where we can get rid of using capital M for the planetesimals, because this m times n is just the mass density of planetesimals that our protoplanet is experiencing as it's plowing through the protoplanetary disk. So for the next little bit, we'll assume that this rho is just a constant quantity. And now we've sort of gotten rid of all usage, all applications of m as the planetesimal mass, because now we can talk about the relative velocity, which is also going to be a constant, and the collision cross-section, which has an r squared. And now, because we have a big planet and a little planetesimal, that collision criterion really depends much more on the big planet's radius. And the gravitational force depends on the big planet's mass. So now everything on the right-hand side here is applying to the growing planet, just like the dm/dt on the left-hand side does. All right. We're also going to assume that the density of the growing planet is sort of constant in time, so that as its mass gets bigger, its radius also gets bigger, and it's basically just mass proportional to radius cubed, so that we can translate back and forth between m and r in these equations. Right, so this now gives us a differential equation that we can solve for m of t or r of t, essentially if they're the same thing. But we can look at different limiting cases just to see what the behavior looks like, because early on, when the protoplanet is still small, its self-gravity is not that important. So this Safronov number is going to be small compared to 1 in the earliest stages. So in that case, the right-hand side of dm/dt is really just the term out front, just the rho v thermal r squared. If the only thing that's changing in time is r squared, that's sort of all we need to worry about. We can convert that to m to the 2/3. So now we really just have a separable differential equation for m of t. You can bring the m to the 2/3 over onto the left, the dt to the right, integrate both sides, and you get m to the 1/3, which coincidentally is just r using the definition. And the right-hand side is just dt, so it integrates to t. So this tells us that the radius is growing linearly with time. That turns out to be a relatively slow phase of growth, because what we see next is when the mass eventually gets big enough that its own self-gravity is important. When the Safronov number gets to be large compared to 1, then the right-hand side changes, right? There's this r squared, and then there's another r squared over here because we have an r cubed in the mass factor divided by an r. Everything else is a constant. So that combines together to give us an r to the 4th. That's an m to the 4/3. And we can do the separable differential equation again. And the solution ends up looking different. Right? It's a similar looking integral, but when you actually solve this back for r as a function of t again, there's a minus sign and there's a 1/t. So this is still an increasing function of time, but it's increasing towards an eventual asymptote, which mathematically is fine to do, but physically we have to start to evaluate what's happening. If you really wanted to just solve the differential equation by itself, not in the two different limits, it gives you an inverse tangent and a tangent as a function of time. So again, it's in the early stages, it's growing as a linear function of time, and then it zooms up towards this asymptotic t infinity time that you can express in terms of the other things. Physically, what this is saying is that this growth in mass starts out slow, but then once the gravitational focusing becomes more important, it grows the cross section and it allows more particles to agglomerate more quickly. And this is sort of a runaway process. And this sort of allows us to go from a 1 kilometer planetesimal all the way up to a 1,000-kilometer sized protoplanet in a roughly in times of only of order, tens of thousands to hundreds of thousands of years, which is pretty fast on an astronomical time scale. Of course, this doesn't include everything, right? Asymptotes mean that something has to break along the way, and this process does in fact stop, and the r as a function of time eventually becomes a constant. And who knows, there's various ideas for what can stop it, right? There can be these mean motion resonances because the mass grows to the point of being able to perturb the orbits of the nearby planetesimals, so they don't just come in as gravitationally focused, they can be scattered away. But also, once the protoplanet has sort of agglomerated everything in its neighborhood, it clears it out, and that density on the right-hand side of the differential equation is no longer a constant. It drops to 0, and the mass gain rate also drops to 0, and everything flattens out. All right, I guess that's all I had to say about that. Hopefully that's an interesting application of this theory when actual impacts are important. The other application of gravitational focusing is this thing that we've observed in the heliosphere called the helium focusing cone. Apologies about the busy figure, but I wanted to put everything in one slide. The solar system, the sun and the planets and all of its magnetic fields are actually in motion relative to the rest of the galaxy. So when we look out in space, there actually is an interstellar flow from our point of view coming towards us from the direction of the constellation of Ophiuchus for some reason. It's just the direction we're moving throughout the galaxy. And there are, when charged particles are coming towards our heliospheric magnetic field, they feel the effects of the magnetic field. They're deflected. They follow these field lines. The magnetic field acts as a shield. But when neutral particles come towards the solar system, they don't feel the magnetic field, but they do end up feeling the gravity of the sun. So for some reason, neutral helium particles have just the right combination of masses and velocities to get essentially focused on the opposite side from the incoming interstellar flow. And there is a slight enhancement of helium atoms in the solar system. So the orbit of the Earth is shown there. The ACE satellite for several years in the late 90s and early 2000s observed the neutral helium, and every year, essentially every 365 days, they would see this peak in neutral helium as the Earth and the spacecraft were passing through this focusing cone. This cartoon comes from a paper on the Messenger spacecraft, which went to Mercury and explored the inner parts of the focusing cone. Yeah, I just wanted to show you this just because this is an interesting way of diagnosing the large-scale interstellar dynamics of the solar system plowing through the galaxy by just seeing this subtle gravitational focusing effect. So yeah, there's a lot of things that can be learned there about our overall home in space here. All right, I guess that is it for this. And I guess that's it for collisional effects, gravitational collisional effects, because the rest of the large N-body lectures will be about collisionless effects.